Deutsch Jozsa algorithm. We will be doing this in Google Colab. Like we did in previous video, we will start with installation of BlueCat. We can do it by using this code !pip install BlueCat. Type the code that was shown earlier in Google Colab. Then click on play button and BlueCat will be installed. We explain the Deutsch Jozsa algorithm, a generalization of the Deutsch algorithm. For function f, which can take two n kinds of inputs, 0.000 to 11.111, we assume that one of the following conditions holds. 1. F x is same for all inputs, namely, f x equals 0 for all x or f x equals 1 for all x. 2. F x is different in half of the inputs, namely, f x equals 0 for 2 and 1 of inputs x, and f x equals 1 for others. This algorithm determines whether oracle is 1 or 2. Above, the circuit is here. It has n qubits 0 and 1 qubit 1 as initial states. Now let's check the states. For the nth qubit, you can see that swapping 0 and 1 changes the overall sign. Next, consider unitless 2. Because f x operates to nth qubit, dividing the summation by f x equals 0 or 1 for each term. We can see that nth qubit is flipped when f x equals 1. Therefore, in the case 1, f x is same for all inputs, each of terms for f x or f x vanish. So, as a consequence, unitless 3 is. In this case, the measurement results from the 0th to nth qubits will all be 0. In the case 2, f x is different in half of the inputs, because the signs are different for f x. Now, consider the probability PR, 0, that all the measurements results from the 0th to the nth qubits are 0. It is squared absolute value of the amplitude of state y equals 0. Because x times y equals 0 when y equals 0, if f x is different in half of the inputs, all the terms cancel each other out, so PR, 0, equals 0. Therefore, the result of measuring up to nth qubits from the 0th will never be all 0. From the above, we can determine the oracle by whether the results of measuring the qubits up to the n1 th bit are all 0 or not. Let's implement this in BlueCat. Let's implement oracle for case 1 and 2, respectively. In the case 1, we invert the nth qubit regardless of the qubits up to the n1 th. In the case 2, we prepare NCX gates such that each qubit up to the n1 th qubit is a control bit and all target bits are the nth qubit. In this case, the nth qubit is inverted for half of the possible values of the qubits up to the n1 th qubit, while remains unchanged for the other half. The following is the main body of the algorithm. First, set the oracles 1 or 2 by random number. This will be the correct answer we want to find. Next, use the Deutsch Jozsa algorithm to determine the oracle. Finally, check if the result of the discrimination and the oracle selected by a random number in advance match. Now we determined the oracle using the Deutsch Jozsa algorithm. That's all for today. Thank you.